Okay, guys. Even though I said I wasn't really going to do any more videos, after the last video, I did a lot of thinking about what exactly I could do. As I said, we only have a choice between bad algorithms and algorithms that don't work at all, like the cross-entropy method from the previous video. Um, this this is a very problematic thing for me. Even if I tried out some other evolutionary algorithm like the OpenAI evolutionary strategy, or I go back to deep reinforcement learning and try out various different methods there and architectures, we'd still get a pretty bad result. At this point, I have so much experience in trying to make deep learning work that I'm sure of this. Deep learning does work in supervised learning domains, but when it comes to reinforcement learning, literally nothing but tabular RL worked for me. One thing that I didn't try is using associative memories as a key value store. I had an idea for this like a long time ago, but the problem with trying to make associative memories work is that they take a lot of compute power, and I mean a lot. In particular, we'll go through this paper later, but let me just illustrate first what the problem is. Okay, here's Excalibur. So let me pause for a bit. Let me talk briefly about associative memories, in particular the modern hope nets we'll be covering in this video. I've known this for a while now, but I've never really seen it used, even though they can be used as dictionaries. I guess it's not really that much different from vector databases. The keys are stored for a modern hope neural network in a n by n matrix where when n is the input size and m is the number of inputs. The values are stored alongside the key, and they could be potentially anything, but in practice they do need to be linearly interoperable. So there'll be a m by k matrix of floats. We could store the policy probabilities and the reward estimates in the value part of the associative memory. So yeah, they're similar to a regular dictionary, but they have a probabilistic basis to them. And so what is the problem? It's related to how these associative memories are indexed into. Like we have a m by n matrix, and it's a dictionary. So if we want to index into it, suppose we have something like a 1 by n vector. Rather, what's the problem? First, let me explain how it works. Suppose we have a 1 by n vector. To index into the dictionary D, based on that m by n matrix, for a modern hope neural net, we do a matrix multiply to calculate a score. Basically, by doing that, if we have one vector and another, we can do a dot product in order to calculate how similar they are to each other. That's kind of like what a matrix multiplication does for multiple inputs. And then once we have that score, let's call that. Let's imagine there it's put in a vector s for many such inputs in the dictionary. We can reconstruct the original input, and in order to do that, we first need to turn that score vector into a probability distribution. And the best way to do that is to use a softmax. The older hope neural networks used a different activation, which was based on the sign, I think, and that activation had a much lower capacity. And as I say here, then to reconstruct the inputs, we can just do we can take that probability distribution, use it to multiply the dictionary, and that would give us another n by n matrix. And then what we have to do is sum up over the outermost dimension to get the reconstructed input. And this paper is from 2020. Here's a blog post associated with it. The energizing function is a generalization of modern Hopf networks, aka dense associative memories, introduced by Krotov and Hopfield. Basically, this coupled network is very much like the transformer. In fact, the way that the transformer does attention is pretty much the same as this associative memory. You can read it this later. Let me just skip to ahead to these images. We start with an illustrated example of a Hopfield network. One input image should first be stored and then retrieved. So for these associated memories, they don't really have a value part. They're using it as a set, a probabilistic set. They take this image of Homer, turn it into a grayscale image, or rather a polar image, into ones and zeros, and then they mask out the bottom part. And then with that bottom part masked out, in other words, these black squares are all, or rather pixels are all zeros right now. You take this image, turn it into a vector, and then multiply it with the dictionary matrix. And then once you do a reconstruction, you'll get back the original uncorrupted image. I mean, in this case, it's very easy to see why this would work, because the dictionary would only have one example, so it would probably return that anyway. But you can put in multiple inputs, and if you do that, I mean, why the hell is it retrieving apart here? I'm not really sure. Okay, so sorry about this. I'm kind of confused myself about this. Okay, are they maybe using the old Hopfield network? I mean, they might be doing that here. Oh yeah. This is with this particular update rule. This is the old Hopfield network. You might learn something like this in neuroscience class. They kind of use it as a model of associative memories. Yeah, I guess it's not good to really skip ahead. So this is with the old rules, which aren't what I've talked about here. It doesn't use a softmax. Instead, it uses this weight matrix, and it uses the sign to update it. Yeah, and this whole network has a very limited capacity, so the reconstruction starts to get corrupted. And here they do some math and basically prove that the storage capacity of the old Hopfield network is a log of the input, something like No. It's not a log, but this thing here. It's a log, a constant, and it's a linear. Yeah, 0.14 times 64 times 64. Okay, so now here we finally cover the modern convolutional networks, aka the dense associative memories. And these have a much higher capacity, like they have an exponential capacity given the size of the input vector. Okay, and we'll skip all this math because I don't want to linger on it too much. And with this particular associative memory, you can see that it reconstructs the Homer exactly. Yeah, it's pretty nice. And this is in fact a component of the transformers model. You can backpropagate through this update rule, but we are not going to be using it like that. As you can imagine, this could be used to actually store the keys for a tabular reinforcement learning algorithm. Instead of using a regular dictionary like we did in the F# series, we could potentially use this as associative memory. And the main problem is that, and why I didn't really bother taking this idea seriously up to now is because, if you're going to do something like tabular reinforcement learning on heads-up no-limit poker, we'd want to have a lot of examples. Like, suppose we want to store 1 million examples in that input in this dictionary. So the m here would be something like 2 to the power of 20, and this n here, let's say it will be like 256 or 512. So it's 2 to the power of 8 or 9. So let's think about the implications of that a little. M by n matrix, and so it's like 2 to the power of 20. Let's calculate real quickly how much that would be. We'll go into Python real quickly. We'll put in underscores like this so we can more easily tell where the tree, so we can more easily separate out the thousands. When I look at a number, I actually have the difficulty figuring out what its scale is, unless it's something like 1,000 or 100 or a 10. But it's kind of difficult for me to just look at a number and see whether it has 8 digits or 9. So that's why I'm putting the underscores here. And the n here will be, let's say, 512. So we can store all the inputs into it. And as we say, we multiply this by 1 by n. So even if we multiply all of this, this isn't even a matrix multiply. If we multiply this by a vector, now we have this huge matrix multiplication to deal with. Like, if you remember, if you have any familiarity with the feed-forward neural networks, you know that we don't use such large layers, but because they take long to calculate. Like, If we have a fifth over layer with an output size of something like 2000, that would be considered to be a large layer. And here we have literally a million. Back when we were testing out the matrix multiplies, we had an 8K by 8K and multiplied it by 8 by 4K matrix, and it took something like 80 milliseconds. So imagine we do this. Okay, let's do it like this. Matmul. Okay, let's not assume a transpose. So we'll do it like this. And this would be a sizable number of operations. But we suppose we have not a batch size of 1, but a batch size of something like, let's see, for the tabular RL that we've been doing, we had something like 256 threads and 24 blocks. And that's something like 3,000 threads. Let's calculate it real quickly. This is the number of threads, 256, that we've been using when training with the tabular CFR, and we had 24 blocks. So it's 6,144 inputs in total. And this is an absolutely huge matrix multiplication. The resulting output would be something like it would be 6 billion elements at the very least. And I'm not sure how long this would take, but probably at least seconds, maybe tens of seconds to churn through all of this. So this is the main problem, and why I didn't really take this method seriously. But now that I've pretty much exhausted all the possibilities, I remembered a few things. For one, I've seen videos online by NVIDIA engineers where they show that as you go from float 32 values to lower precision data types, the energy efficiency of a matrix multiplication becomes exponentially improves. And in particular, if we did something like a 1-bit matrix multiply, if we could even implement it in the card that I have in my personal rig, which is RTX 4060, we could implement a matrix multiply using a bitwise and then pass the result of that into the population count instruction. For the newer cards like H100, the copper cards, let's see, CUDA PTX, they have these specialized instructions for matrix multiplication. Let's see, this. They have these warp group matrix multiply accumulate instructions. And you can see the data types they support here, like true float 32, brainy float 16. They support these 8-bit floating point data types for inference. They support the various sparse data types. They support 8-bit integers. And as luck would have it, they have this single-bit matrix multiply. So, which I'm guessing would be even faster than doing a bitwise and then using a population count. So instead of taking tens of seconds to calculate something like this on a Hopper card, maybe it would still be fast. And it get dozens of milliseconds for to multiply a matrix matrix like this, assuming it's assuming its data type is one bit integer. And once we have this score matrix, this thing, instead of we could also, instead of just multiplying it with the keys, what we could do is multiply with the values and interpolate between them. Like, suppose we have something like let me pause for a bit. Suppose we have an input. This variable. This is the variable imp, and it equals this this vector. And it could really be anything. It doesn't matter. So, since we won't be considering any other possible inputs, we could add it into the dictionary multiple times with different associated values. Like this could be in 0 position. It could have a value of 1. In index 1, it could have a value of 2. In index 2, it could have a value of 3. So we have this kind of dictionary with 3 different keys and 3 different values. Suppose we tried indexing into this dictionary with the input again. Index D. D is the dictionary, imp is key. And then, of course, we have to get the value out. And what we would get is the average of these 3. We do a softmax over the inputs, and we'd see that all of these 3 inputs are basically the same. So we assign 33.3% probability, 1/3 probability on each of these inputs being correct. And when we multiply those probabilities by the values, we get back the 2, the average of these 3. So that means we have a way of probabilistically averaging the values that we add into the dictionary. And we could use that to, for example, average out the reward estimates that we put into it. We could also average out the policy probabilities. So suppose this is something like a reward estimate. We could also have a policy probability like 0.2. I mean, it's not really. We probably need like two actions for these. So let's make this 0, 0, 0, 0. We can even make it something more elaborate. Like let's make it 5. Let's make this 10. So this would be this would have an average of 5. And this would be 0.2, 0.8, for example, 0.4, 0.6. They need to sum up to 1 because this is a probability distribution. And this is, let's say, 0.5, 0.5. And now I'm not really sure what the average of this is. I have to, let's say, this is 2, 4, 5. This is 1.9 divided by 3. Okay, let's take out the calculator. 0.2 plus 0.4 plus 0.5 and well, let's put a parenthesis around this and divide it by 3. 0.36 I mean, we don't need the parentheses here. 0.36, 865, okay. 865, 63. Okay, that seems good. Okay, let's just make it like 64. So it sums up to 1. And yeah, this is basically how we could use this kind of associative memory to do reinforcement learning. Basically, my problem was that when I had the idea for this algorithm, I didn't even have an RTX 4060. I had my old GTX 9070 from like nearly a decade ago. And back then, I didn't have this spiral functionality. I didn't even begin work on Spiral's machine learning library. If we wanted to implement all of this, we'd have to probably do it all in PyTorch. And I mean, could we do these bitwise operations in PyTorch? I'm not sure. We certainly didn't have Poker implemented on the GPU. We'd have to implement it all on the Python side, so it would be very slow to run. And yeah, we have to. Basically, I won't even go further into the details on why something like this would be troublesome and tedious to even test out back then. We simply wouldn't get the performance needed to even try this out. We can do it with small dictionaries, but with small dictionaries, the performance would be horrible. I think for this to work, we need a decent sized dictionary of at least 100,000 and preferably a million or more. So that's the basic requirement to even begin thinking about this associative method. I won't bother thinking deeply about something that cannot possibly work on the correct hardware. And I think a large matrix multiply, such as this one here, realistically, it would still be slow even on an H100. But the matrix multiplications are pretty much the workhorse of the deep learning and modern machine learning. So as the GPUs continue to get better, maybe in the future we'll get in-memory processing. So so pretty much any matrix multiply, as long as it could be fit in memory, could be done in constant time. I know that if we could implement something like this on an FPGA, it could be done in a constant time. So this could be a very powerful method. The size of the matrices being multiplied here are pretty crazy, but on large transformer models with something like 10K sequences, yeah, it could reasonably approach the computational expense of doing something like this here. And the reason why I'm specifically mentioning the H100 is because in the previous video I did say I got a job, and I am 99% sure that everything is going to go okay, and the next week I'm going to be onboarded. And the company does have a lot of very strong GPUs. It's an AI company that deals with that serves the machine learning models and rents out hardware. So I'm going to have very powerful cars to play around with, and we'll be able to test out something like this. We'll do a training loop. based on counterfactual regret, we'll be storing the reward estimates into the values, and we'll be doing the usual counterfactual regret update to do it. In order to get the policy probabilities, we'll have an option of either using something like an argmax on the current rewards to get the policy probability. And there are counterfactual regret variants where instead of using the regret matching function, they simply take the argmax and then average out the policies derived from that. And this is like a simplification of the counterfactual regret algorithm. We could do it like that. We could also take the rewards, do a regret matching function to get the final policy. Actually, no. We could keep around the counterfactual regret values and update them. Yeah, but then we'd be averaging out over them instead of summing them up. That would end up causing trouble. So yeah, maybe the best implementation of this is to do it as simple as possible, and then just take the argmax over the reward estimates, and then to get the final policy, just average those out over the inputs, like by simply indexing into the associative memory. And I think this would be a very powerful method. And the reason for that, to get the reason for that, let's go back to the paper by Jonathan Lin, poker paper. Sorry, let me just pause here so I can track it down again. Yeah, here's that particular paper. And this is where, in this paper, he's using regular tabular CFR with something like a hash set. And he's doing these custom features here using to get the actual key that could be used to index into the hash set. If we tried putting the data raw like we could do in an associative memory, for example, let's consider just a single hand a user could have, and just the two cards just the two hidden cards in his hand. That's 52 times 51 possible combinations. 52 by 51 possible combination just for the hidden card. That's 2,652 combinations. Then suppose we enter the flop. We get 3 new cards which differ from the ones in the hand. So that's 50 times 49 times 48. And okay, this is 311 million. On the turn, we get another card, so that's again we get so again this gets multiplied by 47 because there are 47 possible cards on the turn, and I cannot even tell how big this number is anymore. Let's do something like this, and this is going to be 2 multiplied by 2, and 2 by actually let's multiply by 10 to the power of 6. 10 to the power of 6 is exactly a million, and we need to divide it. Sorry about that. So now we can more easily tell that this is 40 billion and 658 million. So, or rather, let's just say this is 14 billion. Then we have another turn in poker, and this is the river. So this further gets multiplied by 46, and now we have 674 billion possible combinations. And this is just to estimate the hand. We aren't even including all the possible stack sizes and betting histories. I've read that for something like a deep stack poker game, there are more combinations than the atoms in the universe, and the number of atoms in the universe is 10 to the power of 70. So it's impossible to store something like this in computer memory. In computer memory, that's the limit of it is 10 to the power of 10. Because that's 10 million. Maybe 10 to the power of 11 if you have a lot of it. Like hundreds of gigabytes. So instead of storing the exact hand, this is an abstraction that he's using. This is the input, and right now he's checking, is the board paired? Does the board have 3 of the same suit? Check if it's a straight, check if it's a 3 of a kind, and so on. Basically, he's calculating the card rank to get this tuple. And this ends up being a lot less in terms of the number of combinations he's trying to estimate. So let's see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. This could be like 2 to the power of 9 possible combinations that he'd used as input into the dictionary. And that ends up being 512 combinations. And he's also doing a bunch of extra inputs here. Is the board paired? Is the board double paired? Some calculations here. And he is also considering the betting history. He's not even considering the exact values of past betting. He's just counting the number of betting streets where the small blind was raised. He's also calculating the number of streets where the big blind has been raised. And this throws away much of the information about the betting history, most of it. If we had an associative memory like we have here, we could put the hands in exactly as they are. We could put in the betting histories exactly as they are as well. In addition to that, because if you just put in the hands as they are, it will be difficult for the method to learn. So we could, in addition to that, also put in these inputs. We could put in the hand rank as an input in addition to the raw inputs. And I think that would also improve the performance. We can just put in all the extra information, pretty much whatever we want, to tell the model whether there is a flush draw or a straight draw, or what the current rank of the player's hand is. We could also put in just the rank of the board. Oh, I got it seems like, yeah, this is okay. I asked a bit on how to get the catalyst to work, and the repo maintainers here are pretty much ignoring me. Once I join this company, I might actually need to hire these guys as consultants to help me integrate Catalyst into the Spiral's machine learning library. I'm thinking that on this job, I could really upgrade the library to make it possible to easily optimize hand-tune machine learning models that you can find in the wild, like transformer models and image generation models. This could provide value to the company, but it's not a low hanging fruit. Okay, sorry about that. Let's get back to this. But I was saying that we could add many extra additional features in addition to the raw input. And if you have something like, let's say, you have an AA in your canned, and as humans, we can easily tell that this is a pair and this is a very good hand pre-flop. And in another hand, we could also get something like KK. If we didn't include the hand rank as a part of the inputs, and we tried indexing into the associative memory, then these two hands would be completely separate in as far as the model is concerned. But because we have an input telling the model that this is a pair, even if the model didn't see, even if there's no other, even if there are no other examples of their of the player playing KK in the model, he'd be able to tell that this is a good hand simply based on the connection of it being a pair. So that's why I think that in addition to the inputs, adding extra information like the rank of the hand could improve performance significantly. And this is really the great benefit of using associative memories like this to do reinforcement learning. We could put in arbitrary inputs, make also add arbitrary features, and the only thing this would decrease is this input size n. Sure, it might go from being 512 to to 768 if we added a bunch of custom features, but it would be repaid in improved performance. The computational effort of adding extra features into an associative memory doesn't scale like a product. If we added a hand rank to a bucketing method such as this, the number of possible states would automatically be multiplied by 9 because there are 9 possible ranks in poker. But with an associative memory, we could add this very cleanly, and we'd be rewarded for basically adding new features instead of having to do very difficult decisions on how to actually architect this score function here. I think this method is worth a shot. It's basically useless to try getting the optimization-based methods to work. I've tried many deep learning based algorithms. Now I've even tried evolutionary algorithms. They all pretty much die on heads up, no limit hold'em. But if we had this, it would be very simple to implement and train. And we could also implement subgame solving very simply. Because subgame solving, we just have to take in the existing trace and maybe make sure that the very first thread picks the original actions, but all the other threads, that the first thread not just picks the original actions, but also picks the original cards. But all the other threads would be able to sample cards randomly and pick they still need to be pick the original actions for the trace that has been retraced. In other words, that needs to be that the subgame needs to be solved for, but otherwise they'd be free to sample randomly. And we could take a few seconds to do the subgame solving like that. And this would result in a very strong superhuman performance. It will actually be very difficult to implement subgame solving for a tabular agent like this. Over here, this is a full agent that uses abstraction. But for subgame solving, we need to condition it. We need to use the exact inputs as the actual. We need to use the actual raw data as inputs, and that would definitely complicate the implementation significantly. But because in the associative memory version of CFR, we'll be using the raw inputs directly. It will be very easy to do this kind of subgame solving. We won't need to implement a completely different CFR algorithm just to do that. We don't need to look at the tables or sparse trees or whatever. We don't need any of that. The only problem is, as I said, that the matrix multiplies that we need to do will be very large. But this method is worth trying out on the latest generation GPUs. If you look at some of the NVIDIA videos, you'll see slides where they say that they basically made low precision inference much more efficient. And the low precision inference is basically what we are doing here, but we need to implement all of this. So I hope that you've found this video interesting, and in the next videos we'll be beginning work on it. I'll be using the company GPUs to actually test this out. The actual training itself won't take long, but we need the actual asynchronous matrix multiplication instructions in order to do this. It should be pretty interesting to revisit the matrix multiplication on Hopper cards. I myself am interested whether we could just use these shared memory instructions to get a full matrix multiply performance. Like and subscribe. I apologize that I couldn't get the cross-entropy method to work, but maybe it is a little addition to the pool of knowledge of humanity. And if you feel bad that I couldn't do anything in the previous video, make sure to subscribe, make sure to like, and make sure to watch the next video. But because in the following videos, we're going to definitely make a superhuman poker agent. This particular method, I can guarantee that it will work, even though it might end up being too slow to be practical. On future hardware, it definitely will be practical. And if this works, for the first time in my life, I'm going to write an actual machine learning paper telling the world about this wonderful result. See you soon.